asymptote. So we could try plugging in -3 here, but once again you get 0 over 0, which is an indeterminate form, so it's like, oh yeah, that requires more work again. The bottom doesn't factor, but you'll notice the top does factor. Factors into 2 parentheses nicely. You'll notice, oh, same factor top and bottom, so you're going to cross those out. You're left then with just the limit as x approaches -3 of just that, what's left in the parentheses, x minus 2. Plug it in then. Get -2 minus 3, which is -5. That's it. You're done. Looking at the next one up here, your limit as x approaches pi of cosine. Just plug it in. You should know that one from your pre-calc or trig class. And you just get -1. So when you're dealing with trig functions looking for your limits, once again, just plug it in just like you would with a normal problem like you have there on the left. This one here, we're dealing with a root. We tried to plug in 0 for your limit using that direct substitution. Well, that gives us that 0 over 0 stuff, which is an indeterminate form, which means we have more work to do. Well, typically rationalizing the numerator is going to help you out. So that means you got to multiply the conjugate. So we take our original problem, multiply the top and bottom by the conjugate at the top. That's the same as what you have on top, but you just switch the sign from a minus to a plus. Make sure you multiply the top and the bottom both by the same thing. Then you're going to FOIL the top. Remember, in multiplying conjugates, you multiply the first terms. Your outer terms and your inner terms drop out. Then you do your last terms. The bottom, I'm not going to really multiply out. I'm going to basically just rewrite the bottom. You'll notice that the top does simplify. Top just simplifies down to x. So now you have an x times the whole top and an x times the whole bottom. Then you can cross out those x's in front. So you're left with only a 1 on the top, and you're left with your conjugate on the bottom. Now you can actually go ahead and plug in 0. Plug in 0. Work it out. You get 1/2. Now we have the squeeze law. If f is always smaller than g and g is always smaller than h in a particular neighborhood, and you happen to know the limit as x approaches a of f is L, and you know the limit as x approaches a of h, well, therefore, you can imply that the limit as x approaches a of g is also L. Because if you know your two outer limits, and they're both the same thing, the center limit would have to be that. You can actually use the squeeze law to actually prove this right here has a limit of 0. There's details on how to do that on my website if you want. Now, if you look at the graph, we're going to start off with 3 functions of a negative x, which is always less than or equal to your x sine 1 over x is always less than or equal to your x. If you graph your sine or your x, that's what we have in blue on our graphs. If you graph your negative x, that's what we have in red on our graphs. You'll notice that the green is what we're looking at. You'll notice as you come in from each side, all the functions kind of go down towards that 0, 0, the origin. You'll notice the green is always going between the red and the blue. Well, if we just zoom in on this area right here, we get the graph over here to the right. And you'll notice, once again, it continues to oscillate in between the green and the blue. Well, it's obvious to see that the limit of the blue is 0, the limit of the red is 0, and you can see looking at this graph then that the limit of your x approaches 0, of x sine 1 over x also is 0. That's your squeeze law.